At 8:30 in the morning on Monday, August 3rd, 2026, Volcán de Fuego, one of Central America's most active volcanoes, began erupting harder than it had in months. By that evening, it had entered what Guatemala's own volcano monitoring agency calls a paroxysmal phase, its most explosive setting. By Tuesday, pyroclastic flows, superheated avalanches of gas, ash, and rock capable of moving at highway speeds and burning at over 1,800 degrees Fahrenheit were racing down 6 separate ravines on the volcano's flanks. As of this recording, no deaths have been confirmed. Officials credit faster, better coordinated evacuations. A direct, hard-won lesson from the last time this exact volcano did this. Because one of the closed roads, right now, crosses the same ravine that buried an entire town in 2018, killing at least 215 people in a matter of minutes. Here's what makes this moment genuinely more complicated than the eruption is dangerous. Stay away. Scientists studying this volcano say the eruption itself isn't actually the biggest threat. It's what happens after, when millions of tons of loose ash and rock, already piled on slopes steep enough to stand nearly vertical, meet ordinary rain. Let's find out exactly what's happening on Fuego and exactly what far worse actually means. Before we go further, if you want volcano science explained with precision instead of panic, subscribe to Anatomy. Every week, we break down the hidden physical systems shaping our planet. Tectonics, oceans, atmosphere. Using verified agency data instead of viral headlines. Drop a comment and tell us, had you heard of Fuego before this video? Or only its more famous Guatemalan neighbor, Volcán de Agua? Now, let's find out exactly what's happening on this mountain. Let's establish exactly what's happening in order, because the sequence of this eruption, and Guatemala's response to it, is the clearest evidence available for understanding both the immediate danger and the reason officials are handling it so differently than they did 8 years ago. Volcanic activity at Fuego began intensifying on Monday, August 3rd, 2026, at approximately 8:30 in the morning local time. By that evening, according to Guatemala's National Institute of Seismology, Volcanology, Meteorology and Hydrology, universally known by its acronym INSIVUMEH, the eruption had entered a paroxysmal phase, a period of dramatically escalated explosive activity marked by pyroclastic density currents traveling 5 to 7 kilometers down the Seca ravine on the volcano's southern and western slopes, alongside a lava fountain rising some 200 to 300 meters directly above the crater. By early Tuesday morning, August 4th, those pyroclastic flows had expanded into 5, then 6, separate ravines radiating out from the summit. Guatemala's Disaster Response Agency, the National Coordinator for Disaster Reduction, known as CONRED, responded immediately. On Monday, the agency declared a nationwide orange alert, the country's second highest emergency classification, and ordered preventive evacuations from the hamlets of El Porvenir and Las Lajitas in the municipality of San Juan-Alotenango. As the eruption intensified further into Tuesday, officials in the 3 most directly affected departments, Zacatepeques, Chimaltenango, and Escuintla, escalated to red alert, the highest level that exists in Guatemala's emergency framework. Authorities closed National Route 14 at kilometer 83, the entrance to Alotenango, in both directions. A closure carrying specific, hard-earned weight in this exact region, since the route crosses drainage terrain directly connected to the 2018 disaster we'll examine in full in Part 5. INSIVUMEH Director Edwin Rojas addressed reporters directly on Tuesday. Activity at the Fuego volcano continues in a critical explosive phase. His agency's assessment was specific and technical. Ash columns exceeding 5,000 meters, roughly 16,400 feet, above sea level, with authorities warning the elevated activity could continue for another 24 to 72 hours from that point. The human toll from evacuations alone has been substantial. As families were moved from the hamlets closest to the active ravines, Officials reported at least 1,421 people relocated to shelters in the eruption's earliest hours. That figure had climbed to at least 1,699 people by Tuesday, according to CONRED's ongoing count, a number that should be read as a floor rather than a final total, since evacuations were still actively underway as this investigation was compiled. Beyond direct evacuees, the ashfall itself has spread far beyond the volcano's immediate flanks, reaching more than 120 kilometers from the vent, as far as the Department of Hulu and the Mexican border, directly affecting more than 29,000 people and threatening as many as 389,000 people across 618 communities in the broader dispersal zone. Guatemala's Directorate General of Civil Aviation issued advisories covering the airspace west and west-southwest of the volcano, though the country's main international airport in Guatemala City has remained operational throughout. Here is the detail that matters most for understanding why this specific eruption is being handled the way it is. As of this recording, no deaths have been confirmed. Given Fuego's own history, which we'll examine in full, unflinching detail in Part 5, that is not the default outcome for an eruption of this intensity at this specific volcano. Authorities attribute the absence of casualties directly to faster, better coordinated evacuation procedures rebuilt specifically in response to what happened here in 2018. It's worth noting directly because it shapes exactly how urgently CONRED has had to work. Guatemala's evacuation framework is legally non-coercive. Officials cannot compel a resident to leave their home. Evacuation notices function as strong recommendations, which in practice has meant emergency personnel conducting direct, house-to-house visits to persuade residents in the highest risk zones to relocate voluntarily. A genuinely labor-intensive, person-by-person process happening in real time as this eruption continues. So far, this is the story of a serious, actively evacuated volcanic eruption, being managed about as effectively as this kind of event can be managed. But there's a second, less visible threat embedded in this story, one that doesn't end when the ash stops falling or the lava fountain subsides. And it's the specific threat this video's title refers to. The same loose ash and rock currently being ejected onto Fuego's exceptionally steep upper slopes doesn't simply disappear once the paroxysmal phase ends. It stays there, piled at angles steep enough that a relatively modest trigger, a burst of heavy rain, or even, in principle, nothing more than gravity and time, can send it rushing downhill as a lahar, a fast-moving, concrete-dense slurry of ash, rock, and water capable of burying everything in its path. This is precisely the mechanism behind Fuego's deadliest known disaster, and precisely why volcanologists studying this mountain argue that the eruption currently making headlines may not be the most dangerous part of this story at all. To understand why a loose pile of volcanic debris can pose a threat genuinely comparable to, or in some assessments greater than, an active eruption itself, we need the basic vocabulary of what Fuego actually is, how it erupts, and what happens physically to the material it ejects once that material comes to rest on the mountain's own extraordinarily steep flanks. That foundational science is where we turn next. To understand both the eruption currently unfolding at Fuego and the delayed hazard this investigation's title points toward, we need to establish some basic volcanological vocabulary, starting with exactly what kind of volcano Fuego is and why its specific shape matters as much as its chemistry. Fuego is a stratovolcano, the same broad category discussed in this channel's past investigations of Mount Adams and Mount St. Helens. Situated approximately 50 kilometers southwest of Guatemala City, standing roughly 12,346 feet, or about 3,763 meters above sea level. What sets Fuego apart from many of its Cascade Range counterparts is a combination of two factors: extraordinary steepness and extraordinary frequency of activity. Its upper cone carries slopes ranging between 32 and 36 degrees, steep enough that a person would need to actively climb rather than simply walk up much of the terrain. And unlike volcanoes that erupt once every few centuries, Fuego has been in a state of persistent, near-continuous activity for decades, making it one of the most consistently active volcanoes anywhere in the Western Hemisphere. The magma driving Fuego's eruptions is classified as basaltic andesite, with a silica content generally measured between roughly 53 and 57% by weight. This specific chemistry matters directly for how the volcano behaves. Silica content is one of the primary factors governing how viscous or thick and resistant to flow a given magma actually is. Magma in this intermediate compositional range is viscous enough to trap the gas dissolved within it as it rises, building pressure that's eventually released in short, violent bursts. This produces the specific eruptive styles observed at Fuego: strombolian activity characterized by rhythmic, relatively discrete explosive bursts, and volcanian activity involving more forceful, sudden explosions that can eject ash and rock to significant heights very quickly. When these explosions occur, they generate towering eruption columns. The ash plumes reaching more than 5,000 meters described directly in Part 1. Not all of that ejected material stays aloft, however. As the densest, most heavily particle-laden portions of an eruption column lose their upward momentum, they can collapse back down onto the volcano's own flanks rather than continuing to rise, generating what volcanologists call a pyroclastic density current, or PDC. A fast-moving avalanche of superheated gas, ash, and rock, distinct from a simple ashfall in both its speed and its lethality. This specific mechanism, column collapse feeding directly into a PDC, is what's been driving the flows described in Part 1, funneling down Fuego's radial system of ravines, principally the Ceniza, Las Lajas, Honda, Seca, and Zarco drainages, each one a natural channel carved by the same repeated eruptive activity over decades. Now let's introduce the specific physical concept that connects this immediate eruptive activity to the delayed hazard this investigation's title is built around: the angle of repose. Any pile of loose, granular material, sand, gravel, or in this case, volcanic ash and rock fragments, can only be stacked so steeply before gravity overcomes the friction holding individual particles in place, at which point the pile's surface will naturally slump or slide until it reaches a stable angle. That maximum stable angle is called the angle of repose, and it depends on the specific material involved, its particle size, shape, moisture content, and how tightly it's packed together. Here's why this matters so directly for Fuego specifically. The volcano's own upper slopes, as established above, already sit at 32 to 36 degrees, a genuinely steep gradient to begin with. Every eruptive episode, including the one currently underway, deposits fresh ash, rock fragments, and larger volcanic debris directly onto these already steep slopes, adding to a standing reservoir of loose material that sits close to, or at, its own critical angle of repose. This material isn't bonded together the way solid rock is. It's held in place almost entirely by friction between individual grains and fragments, and by a limited, temporary cohesion provided by dry ash acting somewhat like a very weak natural cement. A slope loaded this close to its own stability threshold doesn't require a dramatic trigger to fail. It requires only a relatively modest disturbance. Added weight from fresh material, a burst of saturating rain, or even, in principle, gravity alone acting on an already marginally stable pile, to begin sliding. This is genuinely different from the mechanism driving the primary eruption discussed above. A primary PDC, generated by column collapse, requires fresh magma actively erupting at that exact moment. A secondary mass movement event, triggered by the failure of previously deposited material sitting on an oversteepened slope, requires no fresh eruptive activity at all. The material is already there, already unstable, and already positioned directly above the same ravines and communities threatened by the primary eruption itself. This distinction sets up the single most important, and most genuinely difficult, challenge in monitoring a volcano like Fuego, one we'll examine in full technical detail in Part 4, because a delayed, gravity-driven collapse of previously deposited material doesn't require the kind of deep earth magma movement that produces the seismic signals. Harmonic tremor, long-period earthquakes, that seismologists typically rely on to anticipate volcanic activity. These secondary events can occur without the specific kind of advanced seismic warning a primary eruption often provides. This doesn't mean these events are entirely unpredictable, a point this investigation will address directly and in detail in Part 4. It means predicting them requires fundamentally different monitoring tools than predicting the eruption itself. Finally, let's introduce the specific hazard this delayed collapse most often produces once it's underway, the lahar. When loose volcanic debris on a slope like Fuego's mixes with sufficient water, whether from heavy rainfall, rapidly melting snow or ice, or the sudden failure of a crater lake, none of which is currently relevant to Fuego specifically, but which matters directly for the comparative volcanoes discussed in Part 5. The resulting mixture doesn't behave like an ordinary flood. It transforms into what's called a hyper-concentrated flow, a dense slurry, often carrying sediment concentrations exceeding 60% by volume, with the approximate physical consistency of wet concrete. This isn't a metaphor exaggerated for dramatic effect. It's a genuine, well-documented description of how these flows actually move and what they're actually capable of, and it's the specific hazard this investigation will examine in complete mechanical detail in Part 3. With this foundational vocabulary now established, Fuego's specific composition and shape, the mechanics of primary pyroclastic density currents from column collapse, the angle of repose, and why it makes Fuego's own flanks a standing hazard independent of any single eruption, and the basic concept of a hyperconcentrated flow. We're ready to examine the hidden mechanism at the heart of this investigation. Exactly how a pile of loose ash on a steep slope becomes a lahar capable of erasing an entire town, and why this specific hazard pathway can strike with far less warning than the eruption that created the material in the first place. That's where we turn next. Here is the mechanism that gives this investigation's title its full weight. The material Fuego is depositing on its own flanks right now, during the eruption making headlines today, doesn't need a second eruption to become genuinely catastrophic. It only needs rain. Let's walk through this process step by step, because understanding exactly how a dry, stable-looking slope transforms into a fast-moving, concrete-dense flow is essential for understanding why volcanologists treat this specific hazard with such seriousness. As established in Part 2, Fuego's upper slopes already sit close to their own angle of repose, the maximum gradient at which loose material can remain stable under gravity and friction alone. As rain falls onto this material, water begins filling the pore spaces between individual ash and rock particles. This isn't simply a matter of the debris pile getting heavier, though added weight does play a role. The more consequential effect is hydraulic. As those pore spaces fill with water, the water itself begins bearing an increasing share of the load that was previously carried directly through particle-to-particle contact. This is a well-established principle in soil mechanics called pore water pressure, and its effect on slope stability is direct and severe. As pore water pressure rises, it effectively counteracts the normal stress holding individual particles pressed against one another, the same frictional force responsible for the slope stability in the first place. Pushed far enough, this process can reduce the material's effective shear strength towards zero, at which point the slope doesn't merely erode or slump gradually. It fails catastrophically, and essentially all at once, the entire saturated mass beginning to move downslope as a single, coherent flow. Once that mass begins moving, it undergoes a genuine physical transformation from a solid, if unstable, pile of debris into what fluid dynamicists classify as a non-Newtonian flow. A fluid whose viscosity and behavior under stress don't follow the simple, predictable rules that describe an ordinary fluid like water. A lahar, once mobilized, behaves less like a river and more like wet concrete being poured downhill, thick, viscous, and capable of carrying enormous loads directly within its own moving mass, rather than simply pushing them along the stream. As these flows advance down Fuego's ravine system, They carry more than enough dynamic force to uproot mature trees, damage reinforced infrastructure, and transport boulders up to 1.5 meters across over distances of several kilometers. Critically, this destructive capacity doesn't stay constant as the flow travels. It tends to grow. The moving mass actively scours the channel bed beneath it, incorporating additional sediment, rock, and organic material into itself as it descends, meaning a lahar frequently arrives at a downstream community carrying substantially more volume and more destructive force than it started with at its point of origin, higher up the mountain. Now let's connect this mechanism directly back to the observation raised in Part 2. Why this specific hazard pathway can occur with so little conventional seismic warning. A primary eruption, driven by magma actively forcing its way toward the surface, generates a recognizable seismic signature scientists can monitor for: the deep, harmonic tremor and long-period earthquakes associated with fluid movement through the crust. A delayed slope failure, by contrast, is governed entirely by surface-level physics: gravity, friction, and water. There is no fresh magma involved, and therefore no equivalent deep earth seismic signal for a traditional monitoring network to detect in advance. The threat, in a very real sense, builds silently. Not because scientists lack the tools to study it, but because it operates through an entirely different physical channel than the one conventional volcano monitoring seismology was originally built to watch. This is precisely why this specific style of hazard is sometimes described, even in careful scientific contexts, using language that risks sounding more alarmist than it actually is. Without a magmatic trigger to provide advance notice, a large-scale flank failure can, in principle, occur with comparatively little warning through conventional seismic channels alone. It's important to state directly that this describes a real, genuine limitation of one specific monitoring approach. Not an assertion that these events are inherently unpredictable in every sense. As we'll examine in complete detail in Part 4, an entirely different category of monitoring tools has been specifically developed to close exactly this gap, tracking the mechanical and acoustic signature of a slope failure and lahar directly, rather than relying on the deep earth seismic signals a magmatic eruption produces. There's one more genuinely important physical detail worth establishing here, because it explains why this specific hazard pathway doesn't have a clean expiration date tied to the current eruption, because the debris driving a lahar doesn't require fresh magmatic activity to remobilize, only sufficient water and a slope steep enough to fail. This hazard can persist for a genuinely extended period after an eruption itself has ended. Volcanic debris deposited during an active eruptive episode can remain susceptible to this kind of hydraulic remobilization for months, years, or, in some well-documented cases at other volcanoes worldwide, considerably longer, until either the material has been fully removed by successive flows, has consolidated into more stable ground, or vegetation and soil development have restabilized the slope. This is a critical distinction for understanding this investigation's own title. The immediate eruption currently making headlines will, per INSIVUMEH's own 24 to 72 hour assessment discussed in Part 1, likely subside within days. The material it's depositing right now on Fuego's flanks will remain a genuine hazard for a meaningfully longer period than that. It's worth being precise, in the interest of the same rigor this channel applies throughout, about what connects Fuego's specific situation to the broader global weather pattern this investigation's source material raises. The 2026 Pacific hurricane and typhoon season has produced multiple exceptionally intense storms. Hurricane Genevieve became the first Category 5 storm of the year in the eastern Pacific, and Super Typhoon Dolphin independently reached Category 5 strength in the western Pacific, both fueled by unusually warm sea surface temperatures. Neither storm has made, or is expected to make, direct landfall in Guatemala, and this investigation wants to be precise about what these two facts genuinely establish and what they don't. They're evidence of an atmosphere carrying more available energy and moisture globally, consistent with well-established physics. A warmer atmosphere holds more water vapor, a relationship described by the Clausius-Clapeyron equation, meaning individual rainfall events, when they do occur, are capable of delivering more water more quickly than an equivalent event would have delivered several decades ago. This is legitimate, relevant background context for understanding the broader climate this eruption is occurring within. It is not the same as evidence that either of these two specific, geographically distant storms will directly trigger a lahar at Fuego. The actual, specific trigger this investigation needs to watch for is far more local and far more mundane. Ordinary, seasonal Central American rainfall falling directly onto the debris currently being deposited on Fuego's own slopes at any point in the coming weeks or months. So here is the complete hidden mechanism picture. Fresh volcanic debris, deposited during an eruption that will likely subside within days, sitting on slopes already close to their own stability threshold. A specific hydraulic process. Poor water pressure. Capable of eliminating that stability rapidly and catastrophically once sufficient rain falls. A resulting flow with genuinely extraordinary destructive capacity, growing in volume and force as it travels. A monitoring gap specific to conventional deep Earth seismology, since this entire process requires no fresh magma to occur, and a hazard window that extends well beyond the eruption's own likely timeline, set against the backdrop of a globally energized, moisture-rich 2026 atmosphere. With this mechanism now fully established, we can turn to the specific evidence this investigation has been building toward throughout. The genuinely sophisticated predictive science researchers have developed specifically to close the seismic monitoring gap this section has identified. Technology designed to detect a lahar, not through the earthquake signals it doesn't produce, but through the ones it does. That comprehensive evidence base is where we turn next. Let's now walk through the complete evidentiary record for how scientists are actually working to close the monitoring gap established in Part 3. Because this is genuinely some of the most innovative volcanic hazard science currently being conducted anywhere in the world, and it's happening specifically on Fuego's own slopes. Starting with seismoacoustic monitoring, the primary tool researchers have developed for detecting a lahar directly, rather than inferring its likelihood from upstream conditions alone. Researchers, including geophysicist and National Geographic explorer Gustavo Bejar Lopez, have deployed a dense network of broadband seismometers and small aperture infrasound arrays directly on Fuego's slopes. Instruments buried roughly a meter deep in the volcano's dense rainforest terrain, functioning in a genuinely useful sense as sensitive microphones pressed directly against the ground itself. The physical principle behind this approach is straightforward. A lahar in motion generates a highly distinctive, low-frequency acoustic and seismic signature, produced by the immense friction of dense, boulder-laden mud grinding against and scouring the bedrock of its channel. This signature is genuinely different from the vibrations produced by ordinary tectonic earthquakes, which makes it detectable in principle. But detecting it in practice is complicated by Fuego's own extraordinarily noisy environment. The same ground-based instruments that would detect an approaching lahar are also constantly picking up the ambient rumble of Fuego's own continuous eruptive explosions, wind moving through the forest canopy, and even nearby human activity. To solve this signal processing challenge, researchers have turned to machine learning, specifically adapting a technique called the K-nearest neighbors algorithm. By training this algorithm on a large library of carefully labeled historical seismoacoustic data, drawing in particular on an intense 2022 lahar season that reportedly produced more than 20 distinct, separately documented flow events. Researchers have taught the system to automatically distinguish the specific acoustic signature of an approaching lahar from Fuego's substantial background noise, without requiring a human analyst to manually review the data in real time. Complementing this, infrasound arrays, detecting low-frequency sound waves in the 1 to 100 Hz range, largely below the threshold of ordinary human hearing. Positioned near the primary lahar drainage paths, have demonstrated sensitivity to approaching mass movements at distances of at least 5 kilometers upstream of monitored communities. Combined, This system is reported to provide a genuine early warning window of approximately 20 to 30 minutes before an advancing lahar reaches downstream communities in the Seniza drainage specifically. A window this investigation wants to place directly alongside the mechanism established in Part 3. For a hazard capable of striking with essentially no advance notice from conventional deep Earth seismology, even 20 to 30 minutes represents the specific, measurable difference between an orderly evacuation and a catastrophic loss of life. Now let's turn to a second, genuinely distinct monitoring technique developed through fieldwork by the British Geological Survey, a forensic approach researchers describe as reading a deposit's magnetic fingerprint, formerly termed geomagnetic thermal proxy analysis. This technique relies on a well-established principle in rock magnetism called thermormanent magnetization. Volcanic rocks contain naturally occurring ferromagnetic minerals. When heated above a specific threshold called the Curie temperature, these minerals lose their existing magnetic alignment entirely. As the rock subsequently cools back down below that threshold, the magnetic domains within those same minerals reset, locking into permanent alignment with whatever direction Earth's ambient magnetic field happened to be pointing at that exact moment. In effect, freezing a tiny compass needle inside the rock itself pointed in whatever direction was true at the instant it cooled. Field researchers, working in genuinely hazardous conditions directly within the Seniza and Los Lajas ravines, collect rock and debris samples from recent deposits and analyze the magnetic orientation preserved within them. If the magnetic minerals across a sampled deposit all point in a single, uniform direction, that consistency indicates the material was still hot, freshly emplaced directly from an active eruption column. When it came to rest, since a coherent, single-direction magnetic signature requires the entire deposit to have cooled through its Curie temperature together at roughly the same time, in roughly the same orientation. If, instead, the magnetic orientations across a sampled deposit are scattered and inconsistent, that tells researchers the material was already cold, and therefore already magnetically locked in various earlier, unrelated orientations when it was set into motion. Direct physical evidence that the deposit resulted from the delayed, gravity-driven collapse of older, previously stored material, rather than fresh, eruptive activity. This distinction carries real, practical value for hazard assessment. It allows scientists to directly confirm, after the fact, that a given destructive flow originated from exactly the kind of secondary, magma-independent collapse mechanism described in Part 3, reinforcing, with physical evidence rather than inference alone, that this specific hazard pathway is genuinely active at Fuego and genuinely distinct from the primary eruption. The third major monitoring technique involves high-resolution drone photogrammetry. Repeated aerial surveys, using drones capable of navigating Fuego's steep, rapidly changing ravine terrain more safely than ground-based survey teams could manage, to construct detailed three-dimensional models of the volcano's flanks. By comparing these models across successive survey seasons, researchers can calculate, with genuine precision, the total volume of loose, unconsolidated debris currently accumulated in specific channels like the Seniza and Las Lajas drainages. This transforms hazard assessment from a largely qualitative, experience-based judgment into something closer to a quantified engineering estimate. Rather than simply knowing that a given ravine poses a general lahar risk, civil defense authorities can work from an actual, measured estimate of how much material is available to mobilize, informing more precise judgments about how large a future lahar in that specific channel could plausibly become. Together, these three complementary techniques, real-time seismoacoustic detection powered by machine learning, forensic paleomagnetic analysis of past deposits, and volumetric mapping through repeated drone surveys, represent a genuinely sophisticated, multidisciplinary approach to a hazard that conventional volcano monitoring alone cannot adequately address. It's worth stating directly in the interest of properly calibrated confidence. The specific performance figures cited throughout this section, the 20 to 30 minute warning window, the 5-kilometer detection range, the more than 20 event 2022 dataset, are drawn from field reporting on this ongoing research program rather than from this investigation's own independent verification of each underlying technical detail. The broader picture they support, however, is well corroborated. Fuego has become a genuine testing ground for lahar detection technology precisely because its combination of extreme activity, steep terrain, and directly threatened population has made it one of the most consequential places on Earth to get this specific kind of forecasting right. This complete evidentiary picture. The physical mechanism of slope failure established in Part 3, now paired with the real, active monitoring infrastructure built specifically to detect it, sets up the essential next question this investigation needs to address. How does this current, still unfolding crisis compare to Fuego's own history, and what exactly happened the last time this specific mountain's hidden hazard fully materialized? That historical reckoning is where we turn next. To properly understand why scientists and civil defense officials alike are treating the current eruption with this level of seriousness, we need to examine directly what happened the last time Fuego's delayed hazard fully played out. Because this isn't a theoretical risk model. It's a documented, recent tragedy. On June 3rd, 2018, Fuego underwent a rapid, forcefully escalating eruption that generated exactly the kind of column collapse pyroclastic density currents described in Part 2. Except, on that occasion, these flows evolved with devastating speed into hyperconcentrated flows and lahars as they descended, driven by a combination of the eruption's own intensity and prevailing environmental conditions. The town of San Miguel Los Lotes sat directly within the path of one of these flow channels. It was effectively erased. At least 215 people are confirmed to have died, with additional people never recovered, entombed within meters of the same concrete-dense volcanic mud described throughout this investigation. The disaster remains, by a wide margin, the deadliest volcanic event in Guatemala's modern history, and it stands as the direct, empirical demonstration behind everything this investigation has established about Fuego's secondary hazard pathway. The 2018 disaster's core lesson, examined honestly, is a genuinely uncomfortable one. Fuego's radiating system of ravines. The same ceniza, Las Lajas, Honda, and Seca drainages currently channeling the pyroclastic flows described in Part 1. Doesn't simply carry volcanic material away from the summit into empty wilderness. It funnels that material directly toward inhabited communities that have, in some cases, existed in these exact valleys for generations, precisely because the same volcanic soil that makes this hazard so dangerous also makes the surrounding land exceptionally fertile for agriculture. Placed directly alongside the current, actively unfolding 2026 eruption, this 2018 precedent explains both why authorities have responded with the urgency documented in Part 1, and why this investigation's central scientific concern extends well beyond the eruption itself. The current episode is actively depositing substantial fresh material into these exact same channels, at the exact same time global atmospheric conditions, discussed in Part 3, are producing unusually intense, moisture-laden rainfall events across the broader region. The specific geomechanical conditions that produced 2018's catastrophe. Steep, overloaded slopes, funneling ravines, and directly exposed downstream communities are, by every measure this investigation has established, actively present again in 2026. What's genuinely different this time, and what this investigation wants to credit directly, is the monitoring and response infrastructure built specifically in the years since 2018, the seismoacoustic detection systems, the evacuation procedures that have, as of this recording, kept the current eruption's confirmed death toll at 0. Now let's widen this investigation's lens beyond Guatemala entirely, because the underlying hazard pattern established throughout this investigation, unstable volcanic material accumulating on steep terrain, awaiting a hydraulic trigger, is genuinely not unique to Fuego. It's a documented risk category shared by stratovolcanoes in very different parts of the world, even where the specific triggering mechanism differs. Cotopaxi, in Ecuador, illustrates one such variation directly. Standing nearly 5,900 meters tall, Cotopaxi is capped by an extensive equatorial glacier, meaning its own particular version of this hazard doesn't primarily depend on seasonal rainfall the way Fuego's does, but on rapid ice melt triggered by even comparatively modest volcanic heat. A lahar generated by sudden, large-scale glacial melting at Cotopaxi would draw directly on a far larger, more concentrated water source than ordinary rainfall provides, threatening to sweep through the densely populated Chillo Valley and toward the southern outskirts of Quito, Ecuador's capital. The specific engineering challenge Cotopaxi presents, detecting the onset of rapid subglacial melting quickly enough to warn downstream communities, is different in its details from Fuego's rainfall-driven trigger, but shares the same underlying logic this investigation has established throughout. A volcano's greatest danger doesn't always come directly from its own eruption. Mount Rainier, in Washington state, offers a second, structurally distinct but conceptually related comparison. One this channel has actually examined directly in a previous investigation covering a neighboring Cascade volcano, Mount Adams. As established in that earlier investigation, prolonged exposure to heat and circulating hydrothermal fluid can chemically weaken volcanic rock over thousands of years, transforming portions of an otherwise solid summit into comparatively soft, structurally compromised material. Rainier's own documented history includes exactly this kind of eruption-independent collapse. The Osceola mudflow, roughly 5,600 years ago, and the smaller electron mudflow more recently, both large-scale lahars generated by flank or summit collapse without requiring a fresh magmatic eruption to trigger them. A direct, if geographically distant, parallel to the delayed collapse mechanism established throughout this investigation. Given Rainier's proximity to the densely populated Seattle-Tacoma metropolitan area and the specific downstream communities of Orting, Puyallup, and Sumner sitting directly within historical lahar flow paths, the same underlying category of hazard examined throughout this investigation carries genuinely serious stakes there as well. It's worth being precise about exactly what this comparison does and doesn't establish, in the interest of the same rigor this channel applies to every investigation. Fuego, Cotopaxi, and Rainier are not identical systems, and the specific detection technologies developed at Fuego, tuned to that volcano's particular seismic noise environment, rainfall patterns, and ravine geometry, would require genuine, volcano-specific adaptation rather than a direct, one-to-one transplant to work effectively elsewhere. What does transfer directly is the underlying scientific insight this entire investigation has been built around. That a volcano's most severe hazard isn't necessarily synonymous with its most visible one, and that developing dedicated monitoring specifically for gravity and water-driven mass movements, distinct from conventional eruption-focused seismology, represents a genuinely valuable direction for volcanic hazard science generally, wherever a stratovolcano combines steep terrain, substantial loose material, and a nearby water or ice source. So, having examined 2018's tragedy in full, direct detail, and having placed Fuego's specific hazard pattern alongside genuinely comparable, if not identical, risks at Cotopaxi and Rainier, what's the honest, fully calibrated conclusion this investigation can offer about the broader pattern this current eruption fits into? Fuego's current eruption is not an isolated event in either of two important senses. It's not isolated within Fuego's own history. This exact volcano has already demonstrated, in 2018, precisely the catastrophic potential this investigation has spent 3 sections carefully explaining using precisely this same system of ravines. And it's not isolated globally. The same fundamental hazard category, unstable volcanic material meeting a hydraulic trigger, whether rainfall or glacial melt, threatens comparable communities at volcanoes on entirely different continents. What connects all of this, and what gives this investigation's central scientific story its genuine significance beyond Guatemala's own borders, is that the monitoring science developed specifically to address this hazard at Fuego represents a real, exportable template for exactly the kind of danger this investigation has spent this much time establishing. Not the spectacle of the eruption itself, but the quieter, more patient threat of what the eruption leaves behind. With this full historical and comparative pattern now established, we need to turn to a more immediate, forward-looking question. Given everything this investigation has assembled, what does the evidence actually suggest happens next at Fuego specifically over the coming days and weeks, and what should an informed viewer actually be watching for? That's where we turn next. Let's now turn to what happens next. Separating, as precisely as the evidence allows, the near-term trajectory of the eruption, currently making headlines from the longer, less clearly bounded window during which the Laha hazard this investigation has focused on, will remain genuinely active. Start with the eruption itself. INSIVUMEH's own assessment, delivered directly by director Edwin Rojas and referenced throughout Part 1, placed the current paroxysmal phase's likely duration at 24 to 72 hours from its Monday evening onset, meaning, as of this recording, the most intense phase of this specific eruptive episode is likely at or near its natural conclusion, or will be within the time frame most viewers are likely watching this investigation. This is consistent with Fuego's own well-documented behavioral pattern. As one of the most frequently active volcanoes in the Western Hemisphere, discussed in Part 2, Fuego typically cycles through periods of heightened paroxysmal activity followed by a return to its own, still active but comparatively less intense, baseline behavior, rather than building continuously towards some single, larger culminating event. It's worth being direct about what this expected near-term decline in eruptive intensity does, and does not, mean for the broader hazard picture this investigation has established. It very plausibly means the specific, headline-driving danger of active pyroclastic density currents and heavy, ongoing ashfall will meaningfully ease within days. It does not mean the material already deposited during this episode, the specific hazard at the center of this investigation's title, becomes any less dangerous once the eruption itself quiets down. As established directly in Part 3, that material's own hazard timeline is governed by rainfall and slope stability, not by whether the volcano above it is still actively erupting. Given that distinction, the single most important indicator to watch for in the coming days and weeks isn't further escalation at the summit, it's precipitation. Central America's rainy season runs through significant portions of the year, and any substantial rainfall event over the coming weeks, falling directly onto the fresh debris this current eruption has deposited across Fuego's ravine system, represents the specific, concrete trigger this investigation has identified as capable of transforming today's headline story into a genuinely different and potentially more severe kind of disaster. This isn't a distant, hypothetical scenario. Given Guatemala's climate and the timing of this eruption, it's a realistic, near-term possibility that the monitoring systems established in Part 4 exist specifically to help manage. This is precisely why the seismoacoustic and infrasound monitoring network discussed in Part 4 carries the operational significance it does going forward. As fresh material continues settling across the Ceniza, Las Lajas, Honda, Seca, and Zarco drainages in the coming days, that same network, buried seismometers, infrasound arrays, and the machine learning system trained specifically to isolate a Laha's acoustic signature from Fuego's substantial background noise, will be the primary tool available for providing the 20 to 30 minute warning window. This investigation established directly in Part 4 for any community sitting downstream of a rainfall-triggered flow event in the weeks ahead. There's a second, complementary indicator worth watching directly: continued volumetric mapping through the drone photogrammetry program discussed in Part 4. As this current eruption's contribution to Fuego's overall debris inventory gets surveyed and quantified in the coming weeks, that data will offer civil defense authorities a genuinely concrete, engineering-grade estimate of how large a future Laha in any specific drainage could plausibly become. Information that directly informs how far downstream evacuation and monitoring resources need to extend. It's worth addressing directly with the same honesty this investigation has applied throughout, what remains genuinely uncertain here. No agency or research team reviewed for this investigation has offered a specific probability estimate for when or whether a significant lahar will actually occur in the aftermath of this specific 2026 eruptive episode. This isn't a gap in the available evidence this investigation failed to find. It reflects a genuine, honest limit in how precisely this specific kind of rainfall-triggered hazard can currently be forecast in advance. What can be said with confidence is the underlying conditional relationship this investigation has established throughout. Sufficient rainfall, falling onto the material this eruption is actively depositing right now, meaningfully raises the probability of a significant lahar event somewhere within Fuego's drainage system, without this investigation being able to specify precisely when, exactly where, or how large that event would be. Given all of this, what should an informed viewer actually watch for directly? 3 concrete, checkable developments. First, whether INSIVUMEH's own alert level for the current eruption is lowered in the coming days, consistent with the 24 to 72 hour timeline discussed above, offering the clearest institutional signal that the immediate eruptive crisis has genuinely eased. Second, whether CONRED or INSIVUMEH issue any specific lahar advisory in the weeks following, tied to forecast or observed rainfall over the freshly deposited material. The single clearest sign that this investigation's central concern has moved from a standing risk to an active one. And third, whether any of the specific communities named throughout this investigation, particularly those in the Seniza and Los Lajas drainages, experience an actual lahar event, however contained, which would offer the most direct possible confirmation of everything this investigation has worked to establish about Fuego's delayed hazard. With this forward-looking picture now fully established, a likely near-term easing of the immediate eruption, a longer, rainfall-dependent hazard window that extends well beyond it, and a genuinely sophisticated monitoring system built specifically to provide warning for that longer window. We need to turn to the immediate human dimension of this story. Who is actually living through this crisis right now? What Guatemala's specific legal and logistical constraints mean for how this emergency is actually being managed? And what's genuinely at stake for the communities this investigation has referenced throughout? That's where we turn next. Let's move now from forecasts and monitoring systems to what's actually concretely happening on the ground in Guatemala right now. Because this investigation's careful, technical mechanisms ultimately exist to protect a specific, real population currently living through an active emergency. Start with the immediate, practical reality of Guatemala's evacuation framework, introduced briefly in Part 1, because it shapes everything else in this section. CONRED's legal authority to order evacuations is explicitly non-coercive. The agency can strongly recommend that residents leave a threatened area, but it cannot legally compel them to do so. In practice, this has meant that as Fuego's eruption has escalated through this week, emergency personnel haven't simply issued a public alert and moved on. They've conducted direct, house-to-house visits across the highest-risk hamlets, personally persuading residents to relocate to shelters, family, or other safe ground. This is a genuinely labor-intensive undertaking, and it's worth stating plainly why it matters as much as it does. A non-coercive evacuation system depends entirely on trust, clear communication, and, ultimately, individual residents choosing to leave homes, livestock, and livelihoods behind based on a threat they cannot always see directly for themselves. That this approach has, as of this recording, coincided with 0 confirmed fatalities from this specific eruption represents a genuinely significant achievement in practical, on-the-ground disaster response. Not a guarantee that the same approach will always produce the same outcome, but a real, measurable success worth crediting directly. The communities most directly affected by this week's evacuations, El Porvenir and Las Lajitas in the municipality of San Juan Alotenango, sit precisely within the terrain this investigation has spent 3 sections explaining. Close enough to Fuego's summit to face direct exposure to both primary pyroclastic flows and, in the weeks ahead, the secondary Laha hazard this investigation's title centers on. Beyond these specific hamlets, the roughly 1,600 to 1,700 people evacuated to shelters as of this recording, and the more than 29,000 people directly affected by ashfall across the broader region, represent a population whose daily lives, agricultural work, water access, basic mobility along roads like National Route 14, have been directly disrupted by this eruption, independent of whether a lahar ever actually materializes downstream. The ashfall itself carries its own distinct, less dramatic but genuinely significant set of consequences. Fine volcanic ash is both physically abrasive and a real respiratory hazard, particularly for children, the elderly, and anyone with pre-existing respiratory conditions. Authorities have specifically advised residents across the affected departments to cover water reservoirs, given ash's capacity to contaminate municipal and household water supplies directly. Agricultural land across this fertile volcanic region. Land whose very fertility, as established in Part 5, stems from centuries of exactly this kind of volcanic deposition, faces its own ashfall-related disruption, layered directly on top of the more acute threat facing communities in the immediate ravine paths. Aviation impact rounds out the immediate, tangible disruption this eruption has caused. Guatemala's Directorate General of Civil Aviation issued formal advisories covering airspace west and west-southwest of the volcano, reflecting the genuine, well-documented danger fine volcanic ash poses to jet engines. A hazard this channel has not previously covered in detail, but one aviation authorities worldwide treat with real seriousness, given ash's capacity to melt and fuse within a jet turbine's hot section, potentially causing catastrophic engine failure. Guatemala's main international airport has remained operational throughout this crisis, reflecting careful, ongoing coordination between INSIVUMEH's ashfall modelling and aviation safety authorities, even as the more immediately hazardous airspace closer to the volcano itself has been restricted. Now let's connect all of this directly back to the specific, sharp contrast this investigation raised in Part 1. The difference between this week's outcome and 2018's. In 2018, at least 215 people died in a single, catastrophic event that unfolded with devastating speed. As of this recording, this current eruption, genuinely comparable in its immediate explosive intensity based on the evidence assembled throughout Part 1, has produced 0 confirmed deaths. This difference did not happen by chance. It reflects the direct, measurable product of everything this investigation has documented across Parts 4, 5, and this section specifically. Seismoacoustic monitoring systems that didn't exist in their current form in 2018. Evacuation procedures rebuilt and rehearsed specifically in response to that earlier tragedy's own hard lessons, and a civil defense workforce willing to conduct exhausting, person-by-person outreach rather than relying on a single, broadcast warning alone. This doesn't mean the danger has passed, or that this investigation's own central concern, the Laha hazard examined throughout Parts 3, 4, and 6, has been resolved simply because the immediate eruption has been managed successfully so far. It means Guatemala has demonstrably improved its capacity to manage exactly this category of volcanic crisis, at exactly the moment this investigation's evidence suggests that capacity will continue to be tested, potentially for weeks or months to come, as the material deposited during this specific eruption remains vulnerable to the rainfall-triggered collapse mechanism established throughout this investigation. What emerges from this real-world accounting, taken as a whole, is a genuinely serious, actively evolving emergency. One already producing real evacuations, real economic and agricultural disruption, and real, ongoing hardship for tens of thousands of people, entirely independent of whether the specific, far worse scenario this investigation's title points toward ever fully materializes. And it's a story with a genuinely hopeful, evidence-based thread running directly through it. A community and a government that appear to have taken 2018's terrible lessons seriously and built something measurably better in response. This combination, a real, ongoing evacuation effort constrained by genuine legal and logistical limits, a population of tens of thousands directly disrupted by ashfall and displacement, and a sharp, evidence-based contrast between this week's outcome and 2018's catastrophe, brings us to a necessary final task before this investigation can responsibly conclude: directly auditing the specific claims circulating about this eruption, including making sure this video's own title holds up against everything this investigation has established. That's where we turn next. Before reaching our conclusions, this investigation needs to address several claims and framings directly, including, as always, this video's own title. The first point worth addressing is this video's own central claim, that Fuego's eruption could trigger something far worse. Having now examined this claim from every angle this investigation's evidence allows, the honest verdict is that this framing is genuinely well supported, not overstated. Fuego's 2018 disaster stands as direct, tragic proof that this exact volcano's secondary lahar hazard can exceed the primary eruption's own immediate death toll by an enormous margin. The material currently being deposited during this week's eruption is real, ongoing, and sitting on slopes already documented to be near their stability threshold. This is one of the more straightforwardly accurate title claims this channel has examined. The appropriate caution here isn't about whether the underlying risk is real, but about being precise regarding its timing and certainty, which this investigation addresses directly below. The second point concerns the word could specifically, and it deserves emphasis precisely because it's easy to lose in a dramatic headline. A lahar is a conditional risk, not a certainty. As established directly in Part 6, this investigation found no agency issuing a specific probability or timeline for a significant lahar following this particular eruptive episode. The hazard is real, well documented, and actively monitored. It is not, as of this recording, a confirmed, ongoing event. Treating could trigger something far worse as equivalent to will trigger something far worse would overstate what the evidence currently supports in exactly the direction this channel has cautioned against in past investigations of other emerging hazards. The third misconception concerns the claim, present in some of the underlying source material reviewed for this investigation, that delayed flank collapses of this kind occur with zero seismic warning. As established directly in Part 4, this is only true in the narrow, specific sense of conventional deep Earth seismology focused on magmatic tremor. It is not true of the dedicated seismoacoustic and infrasound monitoring network this investigation examined in detail, a system built specifically because conventional seismology falls short here, and one reported to provide a genuine, if brief, 20 to 30 minute warning window. The honest framing is that this hazard evades one specific, traditional monitoring approach, not that it evades detection entirely. The fourth misconception concerns the connection this investigation's source material draws between 2026's intense Pacific hurricane and typhoon activity. Hurricane Genevieve and Super Typhoon Dolphin, both discussed in Part 3, and Fuego's specific lahar risk. As established directly there, neither storm made or is expected to make landfall in Guatemala, and this investigation found no evidence of a direct, storm-specific mechanism connecting either system to Fuego's own local rainfall. The legitimate, evidence-supported connection is broader and more indirect. Both storms are consistent with a globally warmer, more moisture-laden atmosphere, which plausibly increases the intensity of ordinary regional rainfall events generally. Presenting these two specific, geographically distant storms as a direct trigger for Fuego's lahar risk overstates a connection that the underlying physics supports only in a much more general, background sense. The fifth misconception concerns the extrapolation to Cotopaxi and Mount Rainier discussed in Part 5. The implicit suggestion that the specific monitoring technology developed at Fuego is directly, immediately transferable to these other volcanoes without meaningful adaptation. As established there, the underlying scientific insight, that gravity and water-driven mass movement deserves dedicated monitoring distinct from conventional eruption seismology, is genuinely well supported and broadly applicable. The specific technical implementation, tuned to Fuego's particular terrain, noise environment, and rainfall patterns, would require real volcano-specific redevelopment to function effectively at a structurally different system like Rainier's ice-capped, hydrothermally altered summit, or Cotopaxi's glacially fed drainage network. The sixth misconception is one worth naming because it would represent exactly the wrong lesson to draw from this investigation, having now carefully qualified several of its more dramatic claims. The assumption that because this current eruption has, so far, produced 0 deaths, the overall danger here has been overstated. This would ignore the specific, evidence-based reason for that outcome, established directly in Part 7. A real, resource-intensive, house-to-house evacuation effort, layered on top of monitoring infrastructure that simply didn't exist in this form in 2018. The absence of casualties so far reflects successful, active risk management, not evidence that the underlying risk itself was ever smaller than this investigation has described. The seventh and final misconception concerns the phrase critical explosive phase itself, used throughout this investigation and drawn directly from INSIVUMEH Director Edwin Rojas's own public statements. This is a specific, technical volcanological classification used by Guatemala's own scientific monitoring authority to describe a genuine, measured escalation in eruptive intensity, not a piece of dramatic media framing invented to generate attention. When this investigation, or any responsible coverage of this story, uses this specific phrase, it's accurately reflecting the terminology Guatemala's own volcanologists have chosen to describe what they're observing in real time. What unites all 7 of these points is a pattern slightly different from some of this channel's past investigations. Rather than needing to significantly deflate an overstated title, this investigation has mostly needed to sharpen genuine precision around a title that turns out to be substantially well supported, clarifying exactly what could means, exactly which specific monitoring gap this hazard actually exploits, and exactly how directly connected certain background context genuinely is to Fuego's own specific risk. The real story here, examined with this level of care, doesn't need inflation to be genuinely alarming. A volcano that killed at least 215 people through this exact secondary mechanism 8 years ago is actively depositing fresh material onto the same unstable slopes today, monitored by real scientists using real, innovative technology, while a real, non-coercive evacuation system works, house by house, to keep this week's death toll at 0. That story is already more than sufficient on its own honest terms. With these points addressed directly, we can bring this investigation to its conclusion, including an honest accounting of exactly what remains unresolved as this dossier reaches its final form in the middle of an actively unfolding emergency. This investigation closes in the middle of a story that is, quite literally, still being written, not as a rhetorical device, but as a simple, honest fact about when this dossier was compiled. As of this recording, Volcan de Fuego's paroxysmal phase remains active or has only just begun to ease per INSIVUMEH's own 24 to 72 hour assessment delivered earlier this week. The confirmed evacuee count, standing at roughly 1,700 people as this investigation was written, was still climbing as house-to-house outreach continued across the highest risk communities. And the central, longer horizon question this investigation has spent most of its runtime carefully establishing: whether the fresh volcanic material currently blanketing Fuego's ravines will meet sufficient rainfall to trigger a significant lahar in the weeks ahead. Genuinely cannot be answered yet, by this investigation or by anyone else, because the specific rainfall event that would answer it hasn't happened. If you're watching this after these particular questions have resolved one way or another, INSIVUMEH's and CONRED's own public updates will tell you far more reliably than this investigation, compiled in the eruption's earliest days, ever could. What can be said with genuine confidence, regardless of exactly how this specific chapter resolves, is this: the underlying physical situation this investigation has documented doesn't depend on any single rainfall event to remain real and significant. Fuego's own extraordinarily steep flanks, the specific chemistry of its magma, and its position directly above densely populated, agriculturally vital valleys are permanent features of this landscape, not conditions unique to this particular week's headlines. The material currently accumulating in the Ceniza, Las Lajas, Honda, Seca, and Zarco drainages will remain a genuine standing hazard for a meaningfully longer period than the eruption itself lasts. Whether that hazard fully materializes next week, next month, or gradually stabilizes without ever producing a major event at all. And regardless of how that specific question resolves, one thing is already true, confirmed, and genuinely worth sitting with. As of this recording, a volcano capable of producing exactly the kind of catastrophe that killed at least 215 people in 2018 has erupted again, with comparable immediate intensity, and the confirmed death toll currently stands at 0. That outcome reflects real, hard-won institutional learning. A monitoring network specifically built to hear what conventional seismology cannot. An evacuation system that sends people door to door rather than relying on a single broadcast alert. And a government response shaped directly by the specific, painful lessons of a tragedy this same community lived through 8 years ago. Whatever this specific eruption's longer aftermath ultimately holds, that part of the story is already, genuinely, a success worth recognizing plainly. Gustavo Bejar Lopez and the researchers building Fuego's seismoacoustic monitoring network aren't working to eliminate this mountain's underlying danger. That danger is a permanent geological fact of where Fuego sits and what it's made of, no more removable than the volcano itself. They're working to buy the communities living in its shadow the specific, narrow margin of time, 20 minutes, perhaps 30, that stands between a warning heeded and a tragedy repeated. That margin didn't exist in anything like its current form in 2018. It exists now, actively being tested as this investigation is being written. Check INSIVUMEH and CONRED's own current updates for exactly where this story stands by the time you're watching it. Whether the paroxysmal phase has fully subsided, whether the evacuee count has climbed further or begun coming back down, and whether the rainfall this investigation has identified as the critical remaining variable has arrived yet, or hasn't. But whatever you find there, the deeper story this investigation set out to tell, about a mountain that keeps depositing its own future danger onto slopes steep enough to fail on their own, and about the scientists and emergency workers racing, ravine by ravine, to make sure the next flow finds empty ground instead of a sleeping town, was already true before this week's eruption began, and will remain true long after it ends.